Okay, we're ready to start. So let me just recap a little bit where we are. I always like to recap a little bit from the previous lecture. So in the last lecture, we heard first about the quantity, the tensor, and two ways of writing it. One is usually a capital letter, but that's just convention, with two underbars, two underlines, or as two vectors side by side, which is the dyad. The dyad does not commute. So this is the main thing, is that V is not equal to VA. But it does associate and it does distribute. When we take a vector A written in its most general way in a coordinate system, and a vector M written in its most general way in a coordinate system, we can write them side by side, the indeterminate vector product, and then carry out the various distributive laws, and we get 9 terms. These 9 terms are the fundamental form of writing any tensor in a coordinate system. So when we have a tensor written like a dyad, A next to M, we can write it as writing A in Einstein notation, A sub k, E sub k, next to M written in Einstein notation, M sub w, E sub w. Because these are scalars, we can move them out, okay? Not outside of the summation, but out in front of the dyad, so that we see we have these 9 terms with the 9 combinations of the dyads. E1, 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 E2, E1, E3, E2, E1, E2, 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 E3, E3, E1, E3, E2, E3, E3. So when we have a general tensor written in the capital double underbar form, we can always write it in with respect to an arbitrary orthonormal coordinate system as A with 2 subscripts, and then the 2 subscripts are associated with the unit dyads. Now notice, and I'm going to point this out again, and I sent an email about this, the subscript on the first subscript on the A matches the first of the 2 unit vectors. The second subscript on the A matches the second. That's how we always write it, and that's our convention, first with first, second with second. When we transpose it, that changes, but that's how it always looks. First goes with the first, second goes with the second. And of course, with Einstein notation, we drop the summation signs. So we did a variety of practice problems with this. And then we have the summary of the Einstein notation. We express the unit vectors with arbitrary subscripts, drop the summation signs, and carry out the dot products with the Kronecker delta. So now today we have a few new things to talk about, some of which have already shown up on the homework, so this will be a little bit of catch-up. Let me start. Let's just refresh here for a second. When we're doing a regular dot product of 2 matrices, of 2 tensors, let's say A dotted with C, again, we write it in an orthonormal coordinate system by writing it as A subscript 2 arbitrary subscripts, P, K, let's say, EP, EK. And as I was showing on the other slide, the first goes with the first, the second goes with the second. And then there's a single dot here, C, all new subscripts, I, S, EI, ES. The dot operates between the 2 nearest basis vectors. This becomes the Kronecker delta, Ki, K becomes I. And we get our final result. A, P doesn't change, K becomes I, C, I, S. The ones that are dotted go away. Everything that wasn't dotted stays behind. Now, when I check your homework, I can check these very quickly because I know that these 2, when I dot 2 tensors together, these 2 neighboring ones should be the same. because that's what we did up here. The two neighboring e's became the same subscript. And so, in fact, in this coefficient out front, the two neighboring subscripts become the same. And again, the first goes with the first and the second goes with the second. So once you've done this a few times, that becomes somewhat familiar. This kind of dot product is called the dot product of two tensors. And we've also done the dot product of a vector with a tensor. Let's say v dot c. We can do that one with the same type of methodology. We can also do c dot v, and they won't typically be the same thing. Okay, can you see that they might not be the same thing? Because in this case, the v subscript is going to match the first index on the c. And in this case, the v subscript is going to match the second index on the c. So they're not going to be the same. There's one time when they are the same, and that's when c is symmetric. We'll see that. Okay, so now going on to the new material, there's another kind of a product that we need, and that's called the scalar product of two tensors. So the dot product that we've seen already, between two vectors, that's usually called the scalar product. But between two tensors, there's a new kind of scalar product, or it's also called the double dot product, and it's written with a colon in between the two tensors. So it's A written in Einstein notation, double dot, M written in Einstein notation, and it's defined that you dot the two closest and then the two farthest. So it's like a dot product of the two closest, and then they drop out, and then the two remaining basis vectors dot together. So it's, in this case, P and K are next to each other, so there's EP dot EK. I and M are far apart, but once EP and EK drop out, they get dotted. And the end result is something that has no unit vectors anywhere. It's a scalar. So that's why it's called the scalar product. So it's two tensors multiplying each other with a scalar result. And this scalar result also has two missing summation signs, 1 over M and 1 over K. And that's just some 9 terms added up together in a very particular way. Now, what's that particular way? I can actually do one by hand, and you'll see that even that summation is pretty easy to understand. Let's redo it just for practice. If I take A double dot D, for instance, I write A, I, J, E, I, E, J, double dot D, F, G, E, F, E, G. This becomes the dot product of the two closest together and then the two farthest apart. So that means when I dot these two close together, I get what? Delta JF and delta IG. Okay, so I becomes G, J becomes F. So I get A, I becomes G, J becomes F, D, F, G. So that's the double sum of A, G, F, D, F, G. G goes to 1 to 3, F goes from 1 to 3. So for instance, if I had two tensors A and D, if I wrote them this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's quite a lot of terms there. Okay? So it's going to be when, let's say G is 1, okay? And then F becomes 1, 2, 3. So G is 1, and F becomes 1, 2, 3. G is 1, which means the first subscript on the A and the second subscript on the D are 1. And F goes from 1, 2, 3. Those are the first three terms. A11 times D11. A12 times D21. A13 times D31. So it's just like matrix multiplication. When G becomes 2, everywhere here, these first rows become 2, the second becomes 1. It's this one times that one. And when G is 3, this one times that one. 27 terms. That's 9. That's, let's see. G is 1. Anyway, I'm missing some terms, but they're all, we actually won't be doing this calculation too many times by hand. But we will be doing it in Einstein notation. This is G equals 1, F (1 to 3), and then we have G equals 2. So there's only going to be 9 terms. Not 27, I don't know what I was thinking. 9 terms. This column, that one, this column, that, this row, that column. Now that's what we've covered so far is the dot product of a vector and a tensor, and the dot product of two tensors, and now the scalar product of two tensors. So what we've been learning so far is how to manipulate tensors. I want to now turn back to the beginning. What is a tensor really? Now, what a tensor is really, I haven't actually said yet. What I said so far was that if you took two vectors next to each other and formed the indeterminate vector product, I said that was a tensor. And I've said that if I write something like this, I define it as a tensor, and that in an arbitrary coordinate system, I can write it as API, EPEI. But I haven't really said much about what it's for. And that's my next topic. What is it really? And the answer is, this mathematics we've been learning, this manipulation we've been learning, is the expression of a linear vector function. Stress is a linear vector function, and that's actually what we're after by calling it the stress tensor. So over here, that's what I'm discussing. A tensor is a handy representation of a linear vector function. So there's two words there, linear, well, there's three really, linear, vector, and function, and they all have very precise meaning. Function, if you go back to your first understanding of the word function, it's a mapping. So something goes in, y equals f of x or something. For instance, a scalar function, y equals f of x. Put something in for x, and you get the f back out. When you first learned this back many, many years ago, I imagine, it was a new idea, the idea of mapping x onto a new thing, y. And you had to learn this nomenclature, f of x, etc. The scalar functions you've used a lot. Maybe you've also used vector functions, maybe a little bit less. But a vector function is the same thing. It's a mapping of a given vector onto a new vector. So for instance, when I was doing my examples last time, I was saying that the stress tensor is a mapping of a vector. I'm going to choose a vector choose a plane that I'm discussing. It has a certain unit normal vector. And I want some function to map the choice of this plane to what is the stress on that plane. So I need a function that if I put a unit vector in, which defines this plane, it'll say, OK, the stress is a vector that goes in that direction. If I put in this unit vector, meaning this plane, inside the tabletop, it'll give me a new vector, which is the vector that expresses the stress on that plane. Okay, so that's what we need, in fact, for stress, is a way to map one vector, which in our case is the orientation of a plane, to another vector, which is the stress on that plane. Okay, that's exactly what we need, is a mapping. Now, there's another, so I've discussed two words here, function, which is a mapping, vector, which means it's a function or a mapping that deals with vectors, and linear. Linear is a very precise mathematical word. So the precise meaning of linearity in a function is this mathematical definition. Linear functions, both scalar and vector linear functions, have these two properties. And we have to show that any function has these before we call it a linear function. A linear function is one in which if you put a scalar multiple of the argument inside the function, the mapping or the result is that same multiple multiplied by the function. So f of lambda x equals lambda times f of x. So that ability to take that lambda out makes it a linear function. So for instance, y equals 6x. If I put in 2x, I get 12x, which is, in fact, twice y. So I put in 2x. I got twice y. This is a linear function. Y equals sine of x compared to y equals sine of 2x. Can't take the 2 out, right? It's not equal to 2 times the sine of x. No, 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 no. Not linear. Also, the second criteria of linearity is that when you have an argument of the sum of two arguments, either two vectors or two scalars, the value of the function operates in sort of a distributed way. F of x plus w is f of x plus f of w. So we can go back to my example functions and say f of x, or y, is equal to 6x, and f of x plus, or let's say 3 plus 2, okay? 6 times 3 plus 2 is, of course, 18 plus 12 is 30, right? So we could either do y equals f of 5, which is 30, or y equaled f of 3, f of 2, which was also 30. So certainly that's a linear function. And once again, y equals sine of x doesn't work. Okay? Y equals sine of 3 plus 2 is not equal to sine of 3 plus sine of 2. Not linear. So with this definition of a linear function, this is a general definition, we can just use the hypothesis that a tensor is a linear. Actually, we can just do operations that are related to these two linear properties and show that this business of having an indeterminate vector product is the same as having a linear vector function. So that's what my derivation is next. Okay, so this is my explanation of how tensors are linear vector functions. Okay, so we start off with a linear vector function f of a. Okay, so this is a vector function. So when the argument is a, I get b, and I'm saying it's a linear function, which means I can use these two properties. I can say f of lambda x equals lambda f of x, where x would now be a vector because it's a vector function. And f of x plus w equals f of x plus f of w. All right, so let's try it. We're going to work on the argument a. So a is going to be the argument. It's a vector, so I can write it in any orthonormal coordinate system as the linear sum of three non-zero, coplanar basis vectors. And I can take f of the left side and f of the right side. So f of a equals f of the right side. And either way, I've taken f of a, so it's equal to b. So now you can sort of maybe see where we'll go. This is something we can distribute the function business across. We can take f of this a1e1 plus f of a2e2 plus f of a3e3. And then within each of those, I can take the scalar out, because that's the first linear property, that if there's a scalar on the inside, I can take it out. Okay, so let's do it. All right, there's my left side is f of a. I take f of a1e1, and then I take the a out, because it's a scalar. I take f of a2e2, and then I take the a out, because it's a scalar. I take f of a3e3, and then I take the a3 out, because it's a scalar. So I haven't done anything except apply the linearity rules to the arbitrary argument a written in this coordinate system. So the result is that f of a, which is equal to b, is equal to this linear combination of three new vectors. I don't know what this vector is, but I know it's a vector, because f of anything gives a vector. F is a mapping. It's a function. It's a mapping of a to some new vector. So I'm going to say that f of e1 is v, by definition. And I'm going to say f of a2 is w. And I'm going to say f of a3 is m. Just so that it looks like what it is, which is some vector. Okay? So now I've got that f of a, which is equal to b, is equal to av, a1 times v, plus a2 times w, plus a3 times m. a1 times v, a2 times w, a3 times m. There it is. Now here, I have another step to take. These a's, a1, a2, and a3, are actually kind of special. a1 and a2 and a3 are the coefficients of a in the 1, 2, 3 coordinate system. So because they're the coefficients of a, I can relate them to the dot product a dot e1. A dot e1 is going to be a1. A dot e2 is going to be a2. A dot e3 is going to be a3. Now, just in case that's a little confusing, we can sort of do one out. I'm saying that a dot e1 is equal to something. We can write this out in Einstein notation. APEP dot e1. Okay? That's totally valid. What does this give? Delta P1. Now, 1 is not a summation anymore, right? It's not an I or a K or anything. It's literally 1. So P becomes 1. If by any accident my little mnemonic here had read 1 becomes P, well, it's sort of backwards. Remember, they're both equivalent. So P becomes 1. So this becomes A1, and that goes away, and there you go. This is just something you're used to in a slightly different form. If you have a unit, if you have an A and you have a unit vector direction, then when you take the component of A in the one direction, it's this length here. Or you could go back to the old definition of A dot E1, the magnitude of the first times the magnitude of the second times the cosine of the angle between them, A cosine theta, and any way you slice it, that's the component of A in the one direction. 3 different ways of doing exactly the same thing. So the part we're going to use is that A dot E1 is equal to A1 over here. A2 dot A is equal to A2, excuse me, A times dot E2 is A2. A dot E3 is A3. Now remember, the dot product commutes. So A dot E1 is equal to E1 dot A. But I've written this in a particular order because it's going to work out nicely for my derivation. But they're both correct. Now I take this A1 and put it there. I take this A2 and I put it there. I take this A3 and I put it there. So f of A, which is equal to B, is equal to A dot E1 next to V, A dot E2 next to W, A dot E3 next to M. So I didn't do anything that wasn't invalid. I didn't do anything that you don't know is correct. But look what's happened. Spontaneously, vectors are sitting next to each other without any dots in between them. Okay? The indeterminate vector product has appeared. We have that f of A, which is equal to B, is equal to A dot this indeterminate vector product plus A dot this indeterminate vector product plus A dot this indeterminate vector product. I can factor this A dot part out because of the distributive law, excuse me. You see why we had to study the associative and distributive and commutative laws. I keep referring to them to show you that I'm not making up these rules or introducing any new math. They're just a few assumptions, a few definitions that go with these operations, and the rest comes out. So I'm going to pull, I'm always distributing. Now I'm going to go in the other direction and factor. So when I factor out the A dot, I get f of A, which is equal to B, is A dot the sum of these 3 dyads. The sum of 3 dyads is equal to a tensor. I'll call that tensor M. And so f of A, which is equal to B, is equal to A dot M. That's M now. F of A is equal to A dot M. It's pretty nice. It's pretty sneaky. We didn't do anything except assume that our function was a linear vector function, which meant that we could distribute the functional behavior inside from the f part to the linear combination inside. And just with that capability, we were able to show that a function f, which is a linear function of a vector, can be written just as well as a tensor dotting, a vector dotting with a tensor. It's also true that that there's some vector function that's equal to m dot a, but that's a different vector function. It's still a linear vector function. So at the end of this exercise, we see tensor operations, everything we've been learning, are convenient to use to express linear vector functions. And one of the things we're going to do in this class is derive the Navier-Stokes equations. And in order to derive the Navier-Stokes equations, we need the stress tensor to spontaneously go in there somewhere. And the way it's going to spontaneously go in there is not that I'm just going to make it up. It's going to go in by somewhat similar calculation to the one I just did, where I'm going to talk about the stress at a point and how I need to describe it. And all I'm going to need is the same descriptive power that it's a linear vector function, and I'll be able to do those manipulations, and the stress tensor is going to appear in the momentum balance. All right, so as I said at the first class, one of the motivations, actually second class maybe, one of our motivations is dealing with the Navier-Stokes equation. or this is the Cauchy momentum equation with the stress tensor in it. And what we've learned so far is how to deal with vectors by themselves. This is a vector by itself. And dot products. And tensors. So this is a tensor. This is a tensor. So we're getting very close to being able to do something with the momentum balance. But the next big thing that we need to cover is differential operations. And you can see very clearly why we have to deal with differential operations. So this is our next big topic, which I'm actually not going to start today. But what I'm going to do right now, so this is going to be Friday. And so today what we're going to do is some more miscellaneous definitions with tensors. And a little bit of practice. So we have a couple of definitions that we're going to need. One is the identity tensor. So you're familiar with the identity matrix. The identity tensor is the one that has the identity matrix as its matrix form. It's E1, E1 plus E2, E2 plus U3, E3. It has a 1 in the front here, obviously. In Einstein notation, it's 1 with EI, EI in front of it. So the identity tensor has the same effect as the identity matrix. That is that when you dot the identity tensor with another tensor, you get the tensor back. It's a little bit there's something a little bit new about it in Einstein notation, so we can look at it. EK is how we write the identity tensor. So that's the only tensor where we're not going to make it up as EI, EJ. If you wanted to write it as EI, EJ, then the coefficient is delta IJ. That's another way of writing the identity tensor. But it means the same thing, right? Because I becomes J. And you get that back again. These are the same thing, just a different index used for the calculation. So if you have, I haven't done this yet, so let's not say that. Let's say this. So it's EK dot, now I have to write C in an arbitrary way, PS, EPES. These two together, K becomes P. And we get EP, CP, S, ES. Of course, this is a scalar. It can go anywhere. CPS, EPES. Is that the same thing? Same thing, right? Although we originally chose to write C as PS, the only thing that is necessary is that the first index on the C match the first E, the second index on the C match the second, and the same is true here. The first matches the first, the second matches the second. This is just C. Another definition is the zero tensor. It's pretty obvious. All the coefficients are 0. And then there's the tensor magnitude. This tensor magnitude, you know from doing the homework, is an invariant of the tensor. It makes sense, I guess. Invariant means not changing. It doesn't matter what coordinate system you're in, what the value of the magnitude is. That makes sense from the point of view of a vector as well. The magnitude of a vector is what it is. Doesn't matter what coordinate system you use. And so the same is true for a tensor. If I go back to my stress tensor picture, if there's the stress at a point, and there's some stress tensor, whatever that magnitude is, it doesn't matter what the math is that I use to describe it. It just is what it is. So it shouldn't depend on coordinate system. And this is the definition that's in use for magnitude of a tensor. And there's a typo in the book somewhere, at least one place, where this 2 is either outside the square root. I think it's outside the square root. This is the correct definition. The scalar product over 2 quantity square root is the magnitude of a tensor. So you take A double dot A, carry out the dot products, and you get your final answer. Now this is the one that I thought I was doing earlier, and that's why I was, this is the double product we carry out most often. So let me show it to you, and this will work out a little bit better now. EIEP, AIP, EIEP. Now notice, both in my example on the slide and what I do now is, although I'm writing A again, I'm going to pick new indices because I'm writing it in a new position in the equation. And so I have to pick all new indices. So A, R, T, E, R, E, T. If I chose AIP, EIEP, double dot AIP, EIEP, I'm already saying certain indices match up, which is not true. Okay? The dot product, double dot product, is going to tell me which indices have to match up. So again, the 2 close ones match up, so that's delta PR. And the 2 far ones dot together, that gives delta IT. So P becomes R, and I becomes T. I becomes T, P becomes R, ART. So this is something like the square of a tensor. And this is the one where I can easily do it by looking at the tensor itself. And it's going to be something we use quite a bit in rheology. So the magnitude of this tensor is the summation over T, the summation over R of ATR, ART. So there are 9 terms, and I'm going to multiply each term by its mirror image. So 1, 1 by 1, 1, 1, 2 by 2, 1, 1, 3 by 3, 1. Okay? So 1, 1 by 1, 1, 1, 2 by 1, 2, 1, 3 by 3, 1. So it's 1, 1 by 1, 2, 1, 2 by 2, 1, 1, 3 by 3, 1, 2, 1 by 1, 2, 2, 2 by 2, 2, 2, 3 by 3, 2, 3, 1 by 1, 3, 3, 2 by 2, 3, and 3, 3 by 3, 3. So I'm looking at the diagonal and multiplying by its mirror image across the diagonal. So it's 1 times 1 plus 2 times 4 plus 3 times 7 plus 4 times 2 plus 5 times 5 plus 6 times 8 plus 7 times 3 plus 8 times 6 plus 9 times 9. By mirroring it across the diagonal, because this is TRRT. So this is then, if we were taking the magnitude of a tensor, we would calculate that scalar product, divide it by 2, take the square root, and we'd have it. And then this is the one that showed up in the homework. The transpose of a tensor is exchanging the rows and the columns. And for people just starting with Einstein notation, the most common mistake is the one I describe here below. Do not switch both the rows and the columns and the coefficients. So let me show you that live. If I have a tensor M and I want to take its transpose, first I write the tensor with respect to a coordinate system. So let me call it M, K, T, E, K, E, T. And then I'll transpose it. I recommend that you always transpose by switching the unit vectors. So the answer would be M, K, T, E, T, E, K. Now notice when you have the transpose of a tensor, the first goes with the second goes with the first. That's not how we usually do it, right? We usually say the first goes with the first, second goes with the second. When it's transposed, that flips. So this is the same as flipping the rows and the columns. Which you've seen before. Now, if you made the mistake of flipping it twice, all right, here's my original tensor. If I flip it twice, I get MTK, ETEK. And what is this? It's just M, right? It's just M. Because I could have picked T and K in that order. It was arbitrary that I picked K and T in this order. So M, T, K, E, T, E, K, that's the first going with the first going the second. So let's try one that's a little trickier. Let's try A transpose B transpose. Okay? How do I do it? Okay, so how we write that? AIJ, EIEJ, transpose, IJ, EI. Right? Now we'll dot it with B. Sure, as long as it's anything but I and J, they're the only ones taken up. E, C, E, D. Delta I, C. I becomes C. I becomes C. Everything that wasn't the I and the C stays behind. So the EJ and the ED stay. We have two unit vectors. It's a tensor at the end of the day, right? I became C. The J's stay. B, C, D stays. Everything looks cool. I'll put this scalar out front. A, C, J, B, C, D. E, J, E, D. Now transpose it.
A, C, J, B, C, D, E, D, E, J.
Correct. We keep these exactly the same, and we switch these. If you try to switch it in here, likelihood you'll get it wrong. You can do it, though, by just, again, switching only the J and the D. But that's frankly harder. It's much easier to always switch the basis vectors, because you can always spot those. If you can't spot them, you're probably already too confused to be doing this calculation in the first place. So that's exactly correct. A, C, J, B, C, D, E, D, E, J. That's the correct answer. So there's a C summation. So each coefficient is the sum of 3 scalars. And then they go with the 9 basis vectors that are indexed by ED and EJ. Now, Okay, I have some more to say, so I guess I should get back with the program. I have another good example to do, but maybe we'll see whether I have time for that. So now proceeding with my definitions, now that we know what a transpose is, we can define a symmetric tensor. So a symmetric tensor is equal to its transpose. So MIK is equal to MKI. In matrix form, they're identical across the diagonal. And then likewise, there's something called the anti-symmetric tensor, which M is equal to the negative of its transpose. Since the diagonal doesn't change when you transpose a matrix or a tensor, the only way that it could be M equals minus M transpose is if the diagonal is 0. So all anti-symmetric tensors have a 0 diagonal. And then across the diagonal, they're negatives of each other. The deformation gradient tensor is a symmetric tensor. The vorticity tensor is an anti-symmetric tensor. So these both appear in fluid mechanics. Now, something that we've dealt with a little bit here, but we haven't been explicit about, is called the tensor order. And you can tell that between these three items, scalars, vectors, and tensors, that they're going up in complexity. And so we can name that complexity, and that complexity is called the order of the quantity. And I've been using that term from time to time, I think. And so these quantities, scalar, vector, and tensor, are getting more and more complex in terms of how many components they have in XYZ coordinates. So for instance, scalars have no components. So they have 3 to the 0 components, meaning 1. You know, the scalar 7 is expressed with one number 7. The vector is expressed with 3 coefficients, or 3 to the 1. And the tensors we've been dealing with have 9 coefficients, or 3 to the 2. So this is called the order of the tensor, this coefficient, 0, 1, or 2. And you can actually have, and do have, in physical chemistry, in rheology, third-order tensors that have 27 and then on up into space. So for instance, I can make for you a third-order tensor by just putting 3 vectors side by side. There you go. I've got a third-order tensor. I can also put no dot in between those, and that's a third-order tensor. Look at what this would turn out to be. A, P, K, E, P, E, K times A, M, E, M. It has 3 unit vectors, 27 terms. So A, P, K, A, M, E, P, E, K, E, M is a third-order tensor. We won't see that too much, but it does exist. And then again, the homework showed us this concept of the invariant. The invariants are quantities that are independent of coordinate system. These will be extremely important to us. Because when we make constitutive equations, when we make stress equations that relate deformation to stress, we can only formulate those functions independent of coordinate system. So when we have the rate of deformation tensor, for instance, or a strain tensor, and we want to create a crazy function that'll be correct for no matter what coordinate system we might use, we can only use things that are independent of coordinate system, and these are them: scalar, vector, and tensor invariants. So the magnitude of a vector is its invariant, and the magnitude of a tensor is one of its 3 invariants, and the other 2 are related to these functions. Now, this second invariant is the one that's related to the magnitude because it's got this A double dot product in it. So this is a formal definition, not up to me, so I can't change it to the tensor magnitude. The second invariant is the scalar product, and so the second invariant divided by 2, quantity square root, that's magnitude. So this one's definitely an invariant and related to magnitude. The others are the trace, or the sum of the diagonal components of a tensor, and the trace of the triple, the cube essentially, of a tensor A. Now this was actually the answer, and you feel free to add this to your homework. The reason in our homework, when we calculated the tensor invariance first in one coordinate system and then in the other, The reason why they weren't invariant, which is pretty wrong, is because in the second coordinate system, it was not in an orthonormal coordinate system. These definitions are for orthonormal constant coordinate systems or Cartesian coordinates. So because we transferred it into a coordinate system that was not orthonormal, we couldn't make the trace calculation. Trace calculation in this definition is only for orthonormal coordinates. Kind of makes sense because you can sort of see that if I take a tensor written in one coordinate system and then just, let's say, stretch one of the basis vectors, I'm going to clearly change the trace. So for instance, oops, I'm out of time. If I have a tensor A, which is diagonal, so it's 1 E1 E1 plus 2 E2 E2 plus 3 E3 E3. And if I wrote it in, with respect to a different coordinate system by just stretching one of the vectors, the coefficients are going to change, and so is the trace. I'll finish that up next time. Okay, sorry for going 1.5 minutes over. The digital clock is a tough master.